So good day, student, and welcome to today's section. My name is Isaac Eskin, and I welcome you today. In today's section, we want to look at the concept in numerical analysis, what we call the Gaussian elimination. Grab your book and your pen, sit behind your PC, and let's study. Now, we want to look at the definition for Gaussian elimination. Now, the Gaussian elimination is a method that is used to solve system of linear equations by transforming a matrix into row-echelon form. That is REF, using basic or elementary row operations. So here we are given a system of linear equations, and the goal is to find the values of the variables in the equation. So Gaussian elimination is there to help us get the values of those variables in the equations. Now quickly I'll take you through the steps that we use in doing or solving a system of linear equations using the Gaussian elimination. Now the first thing is to write your system as an augmented matrix. You write a system as an augmented matrix, and then two, you write a matrix in a row echelon form. And the last step, after you get your matrix in the row echelon form, you use what we call the back substitution to find the values of your variables. So I'm going to take example. In fact, we are going to do an example, but let me explain each of the steps we have here and how to do them right. So the first step is we want to write the system. So let's assume that this is a system of linear equations. Let's say we have a1x plus b1y plus c1z is equal to some constant p. Then we have a2x plus b2y plus c2z is equal to some constant q. Then we have a3x plus some b3y plus c3z is equal to some constant r. Now, in forming the augmented matrix, what we want is you want to pick the coefficient of the variables. What are the coefficients? In fact, we have a1, b1, we have c1, we have a2, b2, we have c2, and then we have a3, b3, c3. These are the coefficients of the variables in this system of linear equations. In fact, this is three system of linear equations, right? So those coefficients will form what we call the augmented matrix. So we have a1, we have b1, we have c1, and then we have a2, we have b2, and then we have c2. Then we have a3, we have b3, and then we have c3. Now this becomes your augmented matrix. The coefficient of the variables form what we call the augmented matrix. And so if you have any system of linear equations, you should be able to write its augmented matrix using the coefficient of the variables in the equations. Now the next thing is we have to learn how to write the matrix in a row echelon form. Now in writing a matrix or in changing the matrix into a row echelon form, there are some basic rules we need to go through. So let's learn that independently. So we want to learn how to do or how to write a matrix in the row echelon form. Now let's quickly observe these following rules, right? Now, for a matrix to be in the row echelon form, these rules must be held, or these conditions must be met. And what are the conditions? The first condition says that all non-zero rows are above all zero rows. So this is the first condition that we have. All non-zero rows are above all zero rows. So it means that if there are any rows that are all zeros, in fact all the entries in that rows are zeros, it means they should be at the bottom. Then the others that do not have all the entries being zero should be above that. That's what the first condition means. Don't worry, I'll use an example to explain that. Then the second condition is the leading entry of each non-zero, the leading entry of each non-zero row is to the right. Is to the right of a leading entry in the row above it. In the row above it. That's the second condition. So the leading entry is the value that starts the row. That is what we call the leading entry. And that leading entry of each non-zero row is to the right of a leading entry in the row above it. I'll use an example to show you, but let's list the conditions. Then the last one is all entries below a leading entry. All entries below a leading entry in the column or in a column are zeros. So all entries below a leading entry in a column are zero. Now take note, a leading entry, I should have brought this. So a leading entry is called a pivot. A pivot. So all entries below a pivot, it means in this case, all entries below a pivot in a column are zeros. So that's the third condition. So for example, if I have this matrix, let's say I have A, let's say B and then C. Of course, in this particular first row, our pivot is A. That is the leading entry, right? The leading entry, the first non-zero value that comes in a row. So A is our pivot here. Don't forget that in the conditions, the third one says all entries below a leading entry in a column must be zeros, or they are all zeros. That means that all entries below A should be zeros, right? Let's say I'm just constructing a 3x3 matrix. So all entries below A will be zeros. Now, the next pivot or the next leading entry must be to the right of the leading entry above it. This is the leading entry above this particular row, the second row. So that tells us that the next pivot should be here. Let's call that D. And we make this one E. So the next pivot, which is D, is to the right of the above pivot, which is A. That is what the second condition means. Then don't forget that all entries that are below a pivot in the column must be zeros. When you consider this pivot, which is D, and when you consider that column, the next entry should be zero, right? Then here we can have anything there. Let's call it, let's say P. So this is an example of a matrix in a row echelon form. Now basically, what can you see? You can see that in fact there is some upper triangular something formed here. So basically, when you do a row echelon form, you get an upper triangular matrix. I think that's the basic thing you should take note of. You will get an upper triangular matrix when you change a matrix into its row echelon form. Now, in some books, they will tell you that the diagonal, that is A, D, and P, should be 1. But for row echelon form, it is not necessary. In fact, they make it 1 so that the simplification will be easy. But for row echelon form, it is not necessary. The diagonals can be any non-zero value, right? So this is how we transform or we change a matrix into the row echelon form. Now, before we can get this, we need to do a lot of elementary operations, elementary row operations to get the matrix into row echelon form. And we are going to take an example to work it out. But I just wanted to show you how the row echelon form looks like. So that is a typical example of the row echelon form. So now when we are done writing the matrix in the row echelon form, the last thing we do is what we call the back substitution. All right. So we are going to pick one example and then we walk through to see how we can use the Gaussian elimination to find the values, the values of the variables in that equation. So let's look at this particular example. So in this example, we are given some system of linear equations. In fact, 3 systems of linear equations. So we have x plus y minus z is equal to -2. Then we have 2x minus y plus z is equal to 5. Then we have -x plus 2y plus 2z is equal to 1. So these are system of equations that we have. In fact, 3 system of linear equations that we have on the screen. Our goal is to find the value of x, y, and then z using the Gaussian elimination. That is the goal. We want to solve this system of linear equations using the Gaussian elimination. So remember, the first thing we have to do is to write our augmented matrix. Now I showed you how to get augmented matrix. The coefficient of the variables in the equations form the augmented matrix. So in this case, in the first row, we are going to have 1 because the coefficient of x here is 1, the coefficient of y is 1, and then the coefficient of z here is -1. So we are going to write 1 and then 1, then -1. In fact, let me clear this and then expand this bracket a little bit. We are going to get a 3 because we have a 3 system of linear equations. We are going to get a 3 by 3 matrix. All right. So the next row we are going to have 2, -1, then 1. And with the last row we are going to get -1, 2, and then 2. Now most of the times when we are doing the Gaussian elimination, I bring a long bar, then I write these constant here, -2, 5. I assign it to each of the rows, then 1. Because you are going to perform some basic what I call elementary row operations. That is the reason why I bring these ones. You need to bring them so that at the end of the day, whatever we are going to find for the values, we can just equate them to what we have in our right hand side. All right, so we have formed our augmented matrix now. That is 1, 1, -1, 2, -1, 1, -1, 2, and then 2. So there's our augmented matrix with this right hand side. Now the next thing we are going to do is to put this matrix or this augmented matrix in what we call the row echelon form, and that is where we perform a lot of row operations, elementary row operations, to get this matrix into its row echelon form. All right, so let's learn how to perform these row operations, these basic row operations, to transform this matrix into row echelon form. Now don't forget that in the previous slide, what I just showed you, in fact the idea is to get an upper triangular matrix. So we will try to make this side 0, we make these two sides also 0. That is the goal. So here we will try to make this 0, this 2 0, we'll try to make -1 0, and this 2 also goes to 0. And when we have been able to do that, then we have achieved, or we have been able to turn the matrix into its row echelon form. So basic row operations. The first thing I'm going to do is I'm going to do row 1 minus half of row 2 to replace row 2, right? So that's the first row operation I'm going to do. Row 1 minus half of row 2 to replace row 2. Now the idea is we are replacing row 2 by this operation. So all other rows in the matrix holds, they will stand, but row 2 is what we are trying to change. So we have 1, 1, -1, and then we have our 2 here. Sorry, -2. Row 2 is what we want to change, so we are not going to put anything there. Then row 3 remains the same. So -1, 2, and we have 2 and then 1. Now what we are going to do is row 1 minus half of row 2. So row 1. So 1 minus half of 1, -1. Please pay attention in order to understand what we are going to do. Sorry, it is row 2. So we have 1 minus half of 2. Now half of 2 is 1. So 1 minus 1 will just give us 0 here. Now when we come here, we have 1 minus half of -1. Right? Now what is half of -1? Half of -1 is just -half. Right? It is just -half. So 1 minus -half. So there's already negative there. So 1 minus -half, of course, is going to be +3 on 2. Then the same thing here, we have -1 minus half of 1, which is still half, right? So -1 minus half is going to give us what? -3 on 2. Now here we have -2 minus or being subtracted from, we have -5 on 2 being subtracted from -2, right? We said half of row 2, so half of 5 will be 5 on 2. So -2 minus 5 on 2, and that is going to give us what? That's going to give us -9 on 2. In fact, when you are doing these row operations, you have to be careful because you might easily get confused. And if you miss something, in fact, it's going to affect all the other rows operations you are going to do. So now we have performed the first row operation, and then this is the matrix we have. We have been able to change this figure, which was 2, into 0. The next goal is to make this or this 0. That is our next goal. So let's try to make negative 1 0. In fact, that's going to be simple. In making negative 1 0, we can just do row 1 plus row 3, right? So what we are going to do is, so the next operation we are going to perform, we are going to do row 1 plus row 3 to replace row 3, right? So since that is what we want to do, it means that we will keep all other rows constant. So we have 1 1 negative 1. Then we have our negative 2. We have 0, 3 on 2. We have negative 3 on 2 and negative 9 on 2. Then this is where we want to replace. So we are simply doing row 1 plus row 3. So let's come here. Now row 1, we have 1 plus negative 1. That's 1 minus 1. And this is going to give us 0. Then we have 1 plus 2. We are going to get 3. Then we have negative 1 plus 2, which will give us positive 1. Then the next one is we have negative 2 plus 1, which will give us negative 1. So we have this. Now we have been able to make this 0. So the next target is to change this 3 here into 0. If you are able to do that, now we have our matrix in what we call the row echelon form. So the target is to change this particular 3 to 0. That is what we want to do. So what row operation are we going to do? When you look at it carefully, in fact, we can just do row 3 minus 2 times row 2 to replace row 3. We can just do this, right? So since we want to replace row 3, row 1 and row 2 will be constant. So we have 1 1 negative 1. And we have our negative 2 here. So we have our 0, we have our 3 on 2, and then we have negative 3 over 2. And negative 9 on 2. So we want to replace row 3 by this operation. That is row 3 minus 2 row 2. So let's look at row 3. So we have 0 minus 2 times 0 is still 0. So we have our 0 here. Now look at this side. We have 3 minus 2 times. Don't forget that when 2 multiplies 3 over 2, we are just left with 3, right? When we have 2 multiplying 3 over 2, this cancels this. So we are just left with 3. So here we are going to be left with 3. So row 3 minus 2 row 2 performed on this is going to be 3 minus 3, which will be 0. Then here too, of course, when 2 multiplies this, we get negative 3. So we have 1 minus negative 3, which will give us what? Positive 4. Then the next thing here is we have negative 1 multiplying. Of course, here too, if we multiply negative 9 over 2 by 2, we are just left with negative 9. So negative 1 minus negative 9 will just give us positive 8. And we have this. Clearly, this matrix, in fact, this matrix, that's what I'm referring to, this 3 by 3 matrix, is in what we call the row echelon form. And clearly, you can see that this is an upper triangular matrix. Now, let's check if all the conditions are met. Of course, here, let's go back. Now, in the first condition, all non-zero rows are above all 0 rows. Of course, we don't have any rows carrying all zeros, so that condition is not necessary for what we have now. Now, the leading entry, that is the pivot of each non-zero row, is to the right of a leading entry in the row above it. So let's check this. Now, the first pivot is 1. In the second row, the next pivot is 3 on 2, and that is to the right of the previous one, right? Now, when we move to row 3, then our pivot here is 4. The first leading entry is 4, which is also to the right of the pivot above it, 3 on 2. So you can see that that condition is met. And the next one says all entries below a pivot or a leading entry in a column are zeros. Let's check. This is our pivot and all the entries below it are 0. This is our next pivot. The entries below it in the column is also 0, right? Yes, then this one is just, this is the only entry, the pivot we have here. We don't have anything below it. All right. So all the conditions that are necessary for a matrix to be in its row echelon form have been met here. So this becomes our row echelon form. This matrix becomes the row echelon form matrix. So now that we have it in this form, it is easier to get our values, that is x, y, and then z, by doing what we call back substitution. By doing what we call back substitution. In fact, let me write this matrix again. So we have 1, 1, negative 1, negative 2. Let me rewrite it again. So 1, 1, negative 1, then we have negative 2. And then we have 0, 3 on 2, 0, 3 over 2, minus 3 over 2, then negative 9 on 2. Then we have 0, 0, 4, then 8. So 0, 0, 4, then we have 8. So we are going to do what we call the back substitution. Now, if you remember in matrices, now doing the back substitution, we are going to start from here. If I don't forget that, in fact, this thing looks like this. It is just 1, 1, negative 1, 0, 3 on 2, negative 3 over 2. Then we have 0, 0, 4, multiplying x, y, z, which is equal to negative 2, negative 9 over 2, and then 8. In fact, this is what it means. This thing, this augmented thing we see here, in fact, basically means this, the matrix equation, right? So our goal here is to find x, y, and z. And you know that when we start from, that's why we call it back substitution. When we start from here, it will be very simple, because this means that 0 times x, which is 0, plus 0 times y, which is 0, plus 4 times z, right? So in fact, is that going to be 0 times x plus 0 times y plus 4 times z should be equal to 8, right? This side should be equal to 8. Then the same thing we have 0, I'm just trying to show you, 0x plus 3 on 2y minus 3 on 2z should also be equal to what? Negative 9 on 2. Then the next one should be x plus y minus z should be equal to negative 2. Can you see? So it's like there's a matrix equation. So we are going to do back substitution to find the values of what? Z, x, y, and then z. So let's use back substitution here. In fact, I did this one to help you see it easily, right? Now in doing back substitution, this tells us that 4z is equal to 8. Can you see? Because this is 0 times what? X, 0 times y, and they are all gone because they are multiplying zeros, they are all gone. So basically we have 4z, which is equal to 8. From this equation, 4z is equal to 8. That's how we apply it here. So 4z is equal to 8. Now here, this implies that z is equal to 8 divided by 4, and that is 2. So the value of z is 2. Now the next thing, when we come to this second row, we have 3 on 2y. The x value is 0 because 0 times x, in fact when we come here, 0 times x will just be 0. So we are only left with 3 over 2y minus 3 over 2z is equal to 9 over 2. So that is what we have here. So 3 over 2z is equal to negative 9 on 2. Now we multiply through by 2. If we multiply through by 2, we get 3y minus 3z is equal to negative 9. Don't forget we have found z. Z gave us 2. So we substitute that over there. So 3y minus 3 times 2 is equal to negative 9. And we are left with 3y minus 6 equal to negative 9. We move negative 6 to the other side. So minus 9 plus 6. So we have 3y. What is negative 9 plus 6? That's negative 3. So in order to get y, we divide here by 3, divide here by 3. Then our y is equal to negative 1. So now we have the value of y to be negative 1. The next thing is to find the value of z. Now, the value of x. So finding the value of x, we have x plus y minus z should be equal to negative 2. Right? That's the last equation. So we have x plus y minus z should be equal to negative 2. From this row echelon form matrix, we have x plus y minus z should be equal to negative 2. In fact, you can even see it here. X plus y minus z equals negative 2. Now we know the value of y. The value of y is negative 1, and then the value of z is 2. So we substitute these values into this equation to get a value of x. So x plus, in fact, y is negative 1, so we have negative 1, then minus z. Z is 2, so negative 2, and this is equal to minus 2. This x, negative 1 minus 2 is negative 3, equals negative 2. So we move negative 3 to the other side. It becomes negative 2 plus 3, and x is equal to 1. So finally, our x is equal to 1, our y is equal to negative 1, and then our z is equal to 2. So we have been able to use the Gaussian elimination to get the values of x, y, and then z. I hope that you were able to understand the various steps in using the Gaussian elimination on a system of linear equations to get the values of the variables. So the first thing we said is when you are given the system of linear equations, let me go back. You were given the system of linear equations. The first thing is to write the augmented matrix. And I showed you the augmented matrix are the coefficient of the variables in the equations. And that is what we wrote here. Now, after you do this, you do some basic row operations to get the matrix into its row echelon form, right? And so that's what we did. We performed these. Now, mind you, it does not mean that the row operations should be the same thing. In fact, you can do whatever row operations you want, but at the end of the day, you should end up with the same answers or the same values for x, y, and then z. But these are the basic row operations that I did. You can also try different ones to see if you get the same values of x, y, and then z. So we performed basic row operations, and then we got our matrix in 8 row echelon form, which is this. Then from here, we do what we call the back substitution, where 4z is equal to 8, right? So 4z is equal to 8. We find z from there. And when you find z, you substitute it into the next equation. The next equation will be gotten from here. Then you will be able to find the value of y. So that's what we did. We substituted the value of z into this equation. Then we got the value of y to be -1. Then when you get the value of y and then z, we put it in this equation, that is x plus y minus z, which is equal to -2, to get a value of x, which gives us 1. So basically, this is how we use the Gaussian elimination to solve system of linear equations.